Hello, grade 10s. In today's lesson, we are going to complete the section on the periodic table. And all we still need to cover is the periodicity of atomic radius and ionization energy. There are model answers, there are model ways of answering these questions, and I'm going to take you through that. So firstly, let's define atomic radius. What is atomic radius? Remember definitions, you need to know word for word. Atomic radius is a measure of the size of an atom. The size of the atom is determined by the position of its outermost valence electrons. That means that the size of an atom is based on where its outermost electrons live, which makes sense. Now, if we look at patterns of atomic radius in the periodic table, we can see that atomic radius will get smaller and smaller as we move across a period. So a hydrogen atom is bigger than a helium atom. A lithium atom is bigger than a neon atom. That's almost counterintuitive, and we're going to understand why that is. We can also see that the atomic radius increases as we move down a group. Now, that is less difficult to grasp. We know that the outermost electrons of hydrogen exist in the first energy level, and the outermost electrons of lithium exist in the second energy level. And we also know that each energy level is much further away from the nucleus than the previous energy level, especially if you have watched a video that I posted on a previous lesson where we learned about the different energy levels and the S shells and the P shells. Then you would be able to grasp that each energy level is just so much further away from the nucleus than the previous. So let's see how we go about making sense of these questions and answering these questions. So firstly, why does the atomic radius increase as we move down a group? That's an easier one to answer, so I'm starting with this one. So the outermost electron of hydrogen exists in n equals 1, and the outermost electron of lithium exists in n equals 2. The outermost electron of sodium is in n equals 3. The outermost electron of potassium is in n equals 4, and so on. Each energy level is further away from the nucleus. So n equals 3, which is where sodium's outermost electrons live, is much further away from the nucleus than n equals 1, which is where hydrogen's outermost electron lives. And so that makes sodium a bigger atom than a hydrogen atom. Why does atomic radius decrease as we move across a period? That's a little bit harder to understand because we know that lithium has 3 protons and neon has 10 protons. Lithium has 3 electrons when it is neutral, and neon has 10 electrons. So it almost makes sense that a neon atom should be larger than a lithium atom. We also know that for all of these elements, their electrons, their valence electrons, all exist in n equals 2. So all of their outermost electrons are in the second energy level. Why is it then that lithium is a bigger atom than a neon atom? So let's consider period 3. All the elements in period 3 have their outermost electrons in the third energy level. So we can't explain the size based on the energy level in which the valence electrons live. However, sodium has 11 protons in its nucleus. And if we move across, phosphorus has more protons. It's got 15 protons in its nucleus. So sodium has 11 electrons and phosphorus has 15 electrons. But that does not make it, because it's got more protons and more electrons, that doesn't make it a bigger atom. let's think of the logic. Why is phosphorus a smaller atom than a sodium atom? Well, it's got a nucleus that's got 15 protons. That's got a stronger pull, so that each electron that surrounds the phosphorus atom experiences a stronger electrostatic pull towards the nucleus. In the case of sodium, each electron in the sodium atom experiences a weaker pull because it's only got 11 protons. So 11 protons provides a weaker electrostatic force of attraction relative to 15 protons. Each electron is less attracted to the nucleus of a sodium atom than each electron in a phosphorus atom. It's more attracted to the nucleus because the nucleus has got a bigger positive charge. The stronger electrostatic pull on the electrons makes the atomic radius smaller. So if each electron in a phosphorus atom is more drawn to the center of the phosphorus atom because it has a stronger electrostatic pull because there are more protons in a phosphorus atom, then that results in a smaller atom. Now, here is a type of exam question and the model answer. Which element has a larger atomic radius, silicon or tin? Explain. So let's take a look at the periodic table. Here's silicon, Si, and here's tin, Sn, and they both exist in group 4, and silicon's outermost electrons are in the 3rd energy level, and tin's outermost electrons are in the 5th energy level. So to provide the model answer, which might be out of 4 marks, first thing you would say is that tin has a larger atomic radius or that silicon has a smaller atomic radius. You then need to mention in which energy level the outermost electron of each of these elements exists. So you have to say that tin's outermost electrons or tin's valence electrons are in n equals 5 and silicon's valence electrons are in n equals 3. That would account for another 2 marks. You would then say that n equals 5 is much further away from the nucleus than n equals 3, which what makes tin a larger atom. Or you would say that the 3rd energy level is much closer to the nucleus than the 5th energy level, making silicon have a smaller atomic radius. So that's the 4th mark. So 1, 2, 3, 4. Let's consider the next question. Which element has a smaller atomic radius? Calcium or zinc? Explain. We need to find calcium on the periodic table, and we need to find zinc on the periodic table. And what we note is that both of them have their outermost valence electrons in the 4th energy level in n equals 4. Calcium has got 12 protons in its nucleus, and zinc has got 30 protons in its nucleus. And once we've derived this information from the periodic table, we can answer the question in a model way. So the answer here is that zinc has a smaller atomic radius, or depending on the way the question's asked, calcium has a larger atomic radius. So that would account for 1 mark. Now, we need to mention that both of them have their outermost valence electrons in the 4th energy level or in n equals 4. You have to mention this. You then need to mention that calcium has 20 protons and zinc has 30 protons, or simply you can mention that zinc has more protons in its nucleus relative to calcium. You then need to mention that the electrostatic pull on zinc's electrons is higher, or that the electrostatic pull on calcium's electrons will be lower. But if you're going to mention, especially in this question, you asked which one has a smaller atomic radius, you'd mention that the electrostatic pull on zinc's electrons is higher. You've already explained that it's because zinc has got more protons in its nucleus. That pulls the electrons closer to the nucleus, making the atomic radius smaller. So 1 mark for this, 1 mark for mentioning the energy level, 1 mark for mentioning the number of protons, then the last mark for mentioning which one therefore has a stronger electrostatic pull on the electrons, making the atomic radius smaller, or depending on the way the question is asked, which one has a weaker electrostatic pull, making the atomic radius larger. Again, that's a model answer, and it would be out of 4 marks. Now, that brings us to the ionization energy. And remember that we need to learn definitions, word for word. The ionization energy is the energy needed per mole. We haven't learned what a mole is yet. We'll learn it later, but you still need to integrate it into the definition. To remove an electron from a neutral atom in the gas phase, and that's just because we want to standardize it. We don't want to remove an electron from an ion in the solid phase in one example, and then a neutral atom in the gas phase in another example, because then we're not making a true comparison. These ionization energy values are often just theoretical. And in colloquial terms, in everyday terms, what we're saying is that the ionization energy is how much energy does it take to remove the outermost, easiest electron to remove from an atom. That would be the first ionization energy. The second ionization energy would be, well, how much energy does it take to remove the second hardest electron from an atom? And then the third ionization energy is how much energy does it take to remove the third hardest electron to remove from an atom. But again, this definition needs to be learned word for word, and we're going to see similar logic and similar patterns to the atomic radius logic and patterns. Again, the first ionization energy refers to the energy required to remove the outermost electron from an atom, the easiest one to remove. Then the second ionization energy is the energy required to remove the next easiest, the next outermost electron from an atom, and so on. So let's see the trends in the first ionization energy. First ionization energy means the easiest electron to remove. Now, it looks confusing, but a few things we need to note. This is period 1, hydrogen and helium. This is period 2, starting at lithium and ending at neon. This is period 3, starting at sodium and ending at argon. And remember, we're really zooming in only up to element number 20, and we can see that the first ionization energy of calcium is bigger than that of potassium. Regardless, what we can see is that there is a general upward trend in ionization energy. So if we look here at hydrogen, it takes about 1,200 kilojoules per mole, that's the unit of measurement, to remove hydrogen's outermost electron. It only has one electron anyway. Whereas in helium's case, well, it has 2 electrons in n equals 1, and to remove the first electron from there takes 2,400 kilojoules per mole. So it's almost double the amount of energy as it has taken to remove hydrogen's outermost electron. And the question here is why. Let's take a look at lithium. It takes less energy to remove lithium's outermost electron relative to fluorine's or neon's outermost electron. Now, we can see here that there's a bit of a bump down, so it's not entirely perfect. Also here between nitrogen and oxygen, and that has to do with the S shell and the P shell within an energy level, but we don't need to worry about that. We just need to worry about the general upward trend where it takes less energy to remove an electron from an element in the beginning of a row, in the beginning of a period, relative to an element later on in that period. So we can see that general upward trend. The other thing that we can see is if we consider the start of each period. So period 1 starts with hydrogen, period 2 starts with lithium, period 3 starts with sodium, and period 4 starts with potassium. And we can see also a downward trend, meaning that it takes more energy to remove the outermost electron of hydrogen, which is in period 1, relative to potassium, which is in period 4. Now, we need to understand those patterns and provide model answers. So let's take a look. Why does the ionization energy decrease as we move down a group? So as I move from hydrogen to lithium to sodium to potassium, I'm coming back here to the atomic radius picture. So the question is, why does it take more energy to remove the electron of hydrogen relative to lithium, relative to sodium? It takes less energy to remove the outermost electron of a potassium atom relative to sodium. And I hope that you can take a guess here. If we look at these, hydrogen's outermost electron is an n equals 1, and potassium's outermost electron is an n equals 4, which is much further away from the nucleus, which results in a smaller electrostatic pull on that outermost electron from the nucleus, because each energy level is so much further away from the nucleus. So let's come back to the question. If we read the values off the graph, we can see that the ionization energy of hydrogen is about 1,300 kilojoules per mole, and of lithium is about 700, and then sodium is about 500, and potassium is about 400. So it takes less energy to remove an outermost electron of a potassium atom. And the reason for that is that hydrogen's outermost electrons in n equals 1, and lithium's is in n equals 2, n equals 3, n equals 4, and so on. And each energy level is so much further away from the nucleus. Being further away from the nucleus means a weaker electrostatic pull on the electrons from the protons in the nucleus, which makes electrons that are further away from the nucleus easier to remove. So it takes less energy to remove them. Why does the ionization increase as we move across a period? Again, I'm coming to this atomic radius picture. So why does it take less energy to remove an outermost electron from a lithium atom relative to a neon atom, from a sodium atom relative to an argon atom? Well, the answer is related to what's going on with the atomic radius. Remember that atomic radius decreases because there's a stronger pull on the electrons when the nucleus is larger. So within an energy level, all the outermost electrons of all of period 3 elements exist in n equals 3. But sodium has got fewer protons and argon has got more protons in its nucleus. So therefore, in the case of argon, there's a stronger electrostatic pull on the electrons, bringing them closer to the nucleus. Does it now make sense why it would take more energy to remove an outermost electron from argon relative to sodium? So let's come back to this question. Consider period 3 elements, sodium over here, Na, and phosphorus over here. The ionization energy of sodium is about 500 kilojoules per mole, while the ionization energy of phosphorus is about doubled at 1,000 kilojoules per mole. All of these elements over here have their outermost electrons in n equals 3. However, sodium has 11 protons in its nucleus and phosphorus has got 15 protons in its nucleus. So in the case of phosphorus, each electron that belongs to phosphorus experiences a stronger electrostatic pull towards the nucleus, whereas the electrons of sodium each experience a weaker electrostatic pull. That makes it harder to remove an electron from phosphorus because of that stronger electrostatic pull towards the nucleus, and it makes it easier to remove an outermost electron of sodium because the electrons experience a weaker electrostatic pull. Which element has a higher first ionization energy, silicon or tin? And we answered this question already based on atomic radius. In this case, we would say that silicon has a higher first ionization energy. The reason is that tin's outermost electrons are in the 5th energy level, and silicon's outermost electrons are in the 3rd energy level. Now, it takes more energy to remove an electron from the 3rd energy level relative to the 5th energy level. The reason is that the 3rd energy level is so much closer to the nucleus. That creates a stronger electrostatic pull, being closer to a positive charge if you're negatively charged. So the mark allocation for this question would be 1, 2, 3 for mentioning the energy levels, and then explaining that being closer to the nucleus takes more energy to remove an electron. Then which element has a higher first ionization energy, calcium or zinc? We would answer that by saying zinc has a higher first ionization energy level. We would need to explain that both calcium and zinc have their outermost electrons in the 4th energy level. So that doesn't account for our answer. But calcium has fewer protons in its nucleus relative to zinc. So if zinc has more protons, it means that the electrostatic pull on zinc's atoms is greater, and that makes it harder to remove an electron from a zinc atom. So in terms of mark allocation, 1, 2, 3, the 3rd mark, you can either mention the number of protons or mention simply that zinc has more protons in its nucleus relative to calcium. And then the 4th mark would be to relate that to the electrostatic pull. That brings us to the end of the section on the periodic table. The next section will be on chemical bonding. And once we're done with chemical bonding, that is the end of the module on matter and material.